Okay, good afternoon, everyone. Today, us, we have Dr. Srikant Namodurai. So, I'll introduce the speaker and then we will start. Dr. Srikant Namodurai is currently a data scientist at a startup in Miami and a researcher at Florida International University. Prior to this, he has 10 years of experience in industry working on the IoT analytics and 2-year teaching and research experience in deep learning. Srikanth has Master of Science degree in Electrical and Computer Engineering from University of Louisville. While at Cummins, Srikanth works on IoT architecture and had a patent in this area. He has experience in designing large-scale global IoT system and managing multi-million dollar analytics projects. Srikanth has a graduate certificate in data science from Harvard University. Currently, research include deep learning and image and sensor data. So now I request Dr. Srikanth to please start the lecture. Thank you.
Thank you, Nagendra. Thank you for your kind introduction. Um, as we uh, just as we are getting started, maybe Nagendra, you can tell me a little bit about our audience today. Are most of the audience
Okay, I'll
joining from Pune? Is it
no
mostly
no.
students or yeah?
Most of the audience, the audience is across the India, right?
Great.
And the faculty, mostly the faculty member, and some of the research scholar and the postgraduate students.
Okay. Okay. Great. Good. Very good to know. So let me share my screen. Can you see my screen? Let me know if you can see my screen or not.
Yes, yes, your skin is visible.
Okay, great. Thank you. So, thank you for inviting me for this talk. Um, the focus is deep learning for IoT. As Nagendra has kindly given you all my background, I have worked for several years in IoT, and in the last few years, I've been focusing my energy on deep learning. And I'm very happy to give a talk which combines both these topics. And based on my background, um, since I spend more time in the industry, I think it will be more valuable if I talk uh, in the context of applications or give more examples and talk more about applications. Of course, on the deep learning part, I want to focus more on the basics. Um, I I restricted my presentation to uh, the basics of deep learning and applications and not go into, let's say, emerging or research areas in deep learning. Deep learning and IoT, both of them uh, are really like oceans, two oceans in themselves. There are so many topics one could cover, and uh, I'll do my best in the time we have allotted. And Nagendra, can you confirm till what time do I have? What's
You
the
have 1 hour and 30 minutes, but before also you can finish, no problem.
time? Okay, uh, sure. So for the agenda I have today, first I want to start with a schematic of deep learning IoT system. Excuse me for a typo right there. Okay, let's go. So Start with a schematic. So this is like an overall very general block diagram of what are the different components of a deep learning IoT system. And then uh, a slide with some example applications, especially focusing on the industry. There are several applications of IoT in a wide range of fields, but I wanted to stick to one major example because my experience more closely relates with that area. And I think we can, uh, because even in the industry setting, there are a lot of different applications of deep learning. So uh, it will be uh, good to stick to one topic. And then I want to talk about the background of DL. So people talk about deep learning, talk about artificial intelligence, machine learning, and so many times the terms are mixed up. We'll start with some basic definitions and uh, how deep learning got popular in the recent times. Uh, then a few slides about the underlying algorithm and the underlying approach to deep learning, and a few slides about gradient descent, uh, one of the most important components of a deep learning network or the deep learning algorithm. And then we'll talk briefly about CNNs, RNNs, and autoencoders. Again, CNN stands for convolutional neural network, and RNN stands for recurrent neural network. CNNs are the most popular type of neural networks. So I have a few extra slides on CNN compared to RNNs and autoencoders, where I give a very brief introduction. And once again, I'd like to point out that CNNs, RNNs, and autoencoders are in themselves very deep topics. There are so many different architectures within CNNs and RNNs that one could teach an entire semester on these topics alone. But since I'm I have restricted myself to just a few slides, so the goal you can say is to uh, stimulate interest in these areas, make you familiar with some of the terms, and hopefully that will create interest and make you want to explore and learn more about these topics. In fact, just gradient descent and backpropagation itself is a very wide topic. A lot of research is going on into how to optimize gradient descent and backpropagation. And one of the uh, courses I've taken myself at Florida International University, almost the entire course was uh, teaching the basics of gradient descent and backpropagation. So with that heads up, I'll move forward. We can, if there are um, if there are questions, maybe we'll go through the lecture and then we can take the questions. But if there is something uh, which stops you from understanding the lecture, very important, maybe you can bring it up as well. Okay, so to start off, you can see on the slide on the right side we have uh, a schematic or a representative image of a huge uh, Internet of Things system. Of course, here I'm not representing the communication technologies and the IoT hardware, such as I'm not showing sensors, not showing the particular sensors, but this is, you can say, like a 50,000 feet view um, or a bird's eye view of the overall system. I also represent a cloud here to indicate that especially in Internet of Things, the data from a large number of sensors is collected, uh, mainly since it's internet-based technologies. Mostly the data is saved on cloud-based platforms. So I represent a cloud here. But the other images you see here, like the truck or a mining equipment or an industrial setting, indicate the types of industries and the types of sensors that are used in IoT systems. I'll give an example. For example, the truck you see here is intended to indicate a mining truck. Um, One of the companies I worked for uh, manufactured diesel engines, and these engines went into a lot of different applications, lot of different uh, vehicles of different shapes and sizes. So to give an importance of why predictive analytics or machine learning and deep learning are important in IoT, um, is when a mining truck, for example, um, goes into a a gold mine or a silver mine or a mining any type of metal, any downtime in that truck will cause a lot of loss for the parent company. For example, if a company um, is mining, and I've known from my experience that a 1 hour of downtime can lead to a loss of like $70,000 or $100,000 each time. So companies want to invest in technologies that can predict your failures. Uh, or in industry, if there is equipment that runs 24/7, you want to be able to predict failures or identify corrosion. If there is chemicals involved and metals and there is corrosion involved, you want to be able to identify or automate the process of identification of the corrosion so that you take action in the right time and your equipment does not break down. That's the reason I indicate industrial chemicals here, and same with construction equipment. The different types of sensors involved in this. For example, we want to collect temperature data. We want to collect humidity data. We want to collect the location data, maybe from a GPS, chemical sensors, um, oxygen sensors, etc. Um, Again, to give another example, let us say that a company has a fleet of trucks. Maybe maybe a company owns a lot of Tata or Ashok Leyland trucks, and they're going all across India, but let's say they are seeing a lot of failures. They want to know what is causing failures. So if they are tracking data from oxygen sensors, um, and temperature on the engine, and lot of different parameters in the engines, and lot of different parameters from the trucks, maybe they'll figure out that every time there is less oxygen in the atmosphere, the engine is failing. And they know the engine is failing by looking at the temperature of the engine. So they correlate that whenever there is less oxygen, the temperature of the engine goes up. And then based on the GPS data, maybe they figure out that as long as the truck is driving in uh, Pune or Mumbai, it is doing fine. But let's say if it goes to a hilly region, goes to a high altitude, maybe if it goes to Ladakh, it is failing. So uh, companies need this type of an insight, or this type of intelligence to be able to solve their problems and make sure everything is functioning smooth and they don't lose any money. And the I hope you can see my pointer as well. Um, so the top row you see here is related to that kind of a long-term intelligence where you collect all the data and analyze it from an office location or a command center, and you can look at overall trends. That's one uh, application. A deep learning can be involved there as well, uh, but another place where deep learning can help is real time trying to identify anomalies, trying to predict failures in engines. For example, um, in the example I have given before, if there is something weird going on an engine, so if the operating point, like the temperature or the oxygen levels going out of bounds, uh, we if an anomaly detection system can identify it and maybe send an email to the user or email to the administrator or whoever is responsible. So all the sensor data that is coming in from the various locations is fused together or put in one place on the cloud, and it is input to a a deep learning network. And based on how the network is designed, it can either be used for failure prediction or for anomaly detection, predicting the end of life of particular equipment um, or whatever hardware. So this is the overall flow. You could have another in place of the deep learning network you see here. There could be another machine learning system, but for this talk, we want to focus on the applications of deep learning in IoT. So I have represented specifically a deep learning network. So this example I've given and the couple of uh, use cases I have mentioned with respect to engine failures by location or at an altitude, that is, it is all examples of industrial IoT, um, or when you combine IoT and deep learning, machine learning, it comes under the umbrella of Industry 4.0, uh, which is uh, supposed to be one of the biggest applications of IoT. Um, Very important. Governments across the world are investing into it. Uh, in India also, we expect a uh, lot of users, lot of money, and lot of research into Industry 4.0 in the coming years. And the other areas where such system could be uh, used is in a wide range of applications such as agriculture, smart cities, and healthcare. You can imagine just like this system. For example, in agriculture, there are several sensors such as in temperature, humidity, and let's say nitrogen levels in the soil, or measuring various nutrients and different types of chemicals in the soil, and also measure the sunlight uh, and various different parameters which are important for agriculture. And um, you still feed that data to a machine learning or a deep learning network, and it'll help predict what is the future yield of the crop, what is the is there you know do these parameters indicate there's an anomaly, so should the farmer be prepared for something else? Or in terms of smart cities, how do you collect sensor data and then maybe use it to regulate traffic or predict how many uh, you know pedestrians will be there, and automatically regulate how long you will switch on or off a traffic light. Now, several applications. So I'll stop the examples now and then uh, show a more deeper look on the next slide. Instead of looking at uh, the overall system, we look at a view which shows only the data flow in this system. Okay, so here, the lower half of the slide, you can see the flow of the data starting with the sensors. Then we are doing data acquisition, and and then there is a pre-processing stage where activities like denoising or dimensionality reduction are done, and then training takes place. Um, when we collect data from the real world, such as an industry or a on highway truck, um, excuse me. So the data is usually very noisy. So a denoising can really help improve our results in several cases. And similarly, when you collect data from hundreds of sensors, let's say different types of sensors, uh, different types of chemical sensors, audio, vibration sensors, and things like that. And theoretically, let's say you end up with 300 different parameters. Uh, in some cases, some networks can handle it. In some cases, if the training of a neural network is happening on a resource constrained device, like on the edge, for example, and not on a workstation, in that case, we want to reduce the dimensionality. We want to go from 300 variables to maybe 5 variables. That's where dimensionality reduction techniques can help. And once we have trained the network, we can use it for failure applications such as predicting failures, anomaly detection, and predicting the remaining useful life of a device or equipment. And and of course, the way you train your network and the way you optimize it, the parameters you use, the number of layers or uh, the learning rate you use depends upon the application uh, that you intend. And in the top half of the slide, you can see various tasks and what type of deep learning architecture is suitable. I know that I have not yet talked about the basics of deep learning, but think of this like a teaser to give you a heads up about what are the different types of deep learning architectures. For example, let's say we want to do denoising. When we collect the data, uh, and we want to do denoising, it's it's under a broad category of problems termed as unsupervised learning. I'm guessing in the series of lectures you have been attending, um, my guess is you had other lectures about machine learning and potentially seen supervised and unsupervised learning already. So I am not going into a lot of detail about the types of learning. So and for unsupervised learning, typically autoencoders are a great uh, are a is a great architecture which is highly suitable for unsupervised tasks such as denoising and dimensionality reduction. And for forecasting, um, certain tasks like forecasting or detection of uh, structural damage, for example, use supervised learning, and um, typically uh, CNNs, RNNs, that is convolutional neural networks, and recurrent neural networks are applied more in those cases. Whenever you see the term ANN, it refers to an artificial neural network, or typically it is also referred to as a fully connected network. In the following slides, we will see what that means, but uh, for now, enough to remember it stands for an artificial neural network. So, and a task like anomaly detection could be supervised, unsupervised, or semi-supervised, and we typically use RNNs or autoencoders for such tasks. Um, any questions so far? Anything do you want me to uh, take a small break for questions, or do we keep going?
I hope, sir, there is no question. You can continue, and
Okay,
at the end of the session, we will take the questions.
perfect. Okay, thank you.
Thank
Okay, so now we take a step back. We've talked about a few applications and um, hope have raised your curiosity enough to learn more about deep learning from those examples. And now I want to talk a little bit about the basics and the giving a reference to my source here. Um, Most of the content on these slides comes either from a tech, there's a couple of textbooks I refer and a couple of papers. In the end, there is a reference slide where you'll see that at the end. But the next few slides come from this great textbook uh, by Francois Cholet called Deep Learning in Python. So first of all, like I mentioned, there uh, when you see research papers, you see white papers or see any news articles, several times uh, artificial intelligence, machine learning, deep learning, these terms are used very interchangeably, and there is no clear uh, definition that is followed. But it's it's very useful to remember this relationship that deep learning is a subset of machine learning. So the techniques and algorithms used in deep learning are a subset of all the machine learning algorithms, and machine learning itself is a subset of artificial intelligence, of the term artificial intelligence. And um, for example, artificial intelligence, the term, the concept started around 1950s, and the goal of AI is to automate intellectual tasks that are normally performed by humans. So it is a very broad definition, and there are approaches in artificial intelligence that are that do not involve machine learning. So in the initial days, there was a lot of rules-based learning, which is also called symbolic AI, that people tried. It did not. It gave some results, but it never gave great results. And with the advent of machine learning techniques, um, the researchers and the users started seeing way better results. And so the focus shifted to machine learning. And then once deep learning came along, the results or the performance got even better. And there's a lot of focus on deep learning. But still, in the literature, um, or even job postings, you will see this term artificial intelligence a lot. When they say AI, in the recent times, they're either referring to machine learning or deep learning, and not symbolic AI, but still the very broad term of artificial intelligence is used by everyone. So machine learning is not rules based, which means to say uh, the uh, the representations that are learned or the relationships that are learned, they are not hard coded, and the algorithm is learning from the data by itself. And the user is only providing examples of relevant tasks and expected outcomes. When I say expected outcomes, it's the labels or this refers to supervised learning. And the system learns the rules for associating the examples and the outcomes by itself. So uh, it is, and mostly these algorithms are based on statistics, and um, the algorithm is trying to map the examples to outcomes based on certain statistical rules. Uh, Excuse me for a second here. I'll just I'll just restart. Sorry about that. Hope you can see me. Are you able to see my slides again?
Yes, sir.
Okay, great. So if we are not hard coding our hard coding any rules to ML algorithms, what is the input from the users? So, uh, three important components. One is providing the samples, providing the labels or the expected outcomes. Of course, this is relevant only to supervised learning. And then a cost function or an error function, something like a root mean square error. By RMSE, I mean root mean square error here. So the user chooses the inputs such as what optimizing function to use, what cost function to use, and provide input data and labels. And then the machine learning algorithm is doing the rest. And in this context, uh, what is the underlying goal uh, for this machine learning algorithm is to learn a certain way of representing the data. For example, as simple as if you see a regression, you're trying to represent the data using a straight line or a polynomial, and you're trying to learn the coefficients that represent the straight line or the polynomial. And when we say learning representations, it's a way to encode the data. So, in one way, if you have, uh, 10,000 data points, and you're representing it by a polynomial which has, let's say, even 10 coefficients. So you are in a way encoding 10,000 samples into 10 parameters. So you can think of a machine learning model or a deep learning model as a way of encoding the data. And all ML algorithms consist of finding representations or transformations of data based on the problem at hand. So the type of representation you use, the type of encoding that you achieve is based on the problem you're trying to solve. There is no one right model or one right representation of the data. It all depends upon what problem you're trying to solve. And coming to deep learning in this context, um, again, deep learning is also uh, a way, provides a way of learning representations from data or a way of encoding the data. And there is a mathematical and it's also a computational framework. It's a mathematical and computational framework for learning representations from data. But when we hear the term deep learning, what it indicates is first there is neural networks involved, uh, and then there are several layers of nodes in that neural network. Learning is happening through those several layers, and by the when you reach the final layer, you achieve that encoding or that representation. And the term deep is used because there is a certain hierarchical learning. There is a certain hierarchy of features in those layers. When we see an image of a neural network, we'll talk more about that hierarchy. But each each layer learns from its previous layer and learns a more meaningful feature compared to its previous layer. Once again, this will make more sense when you see one of the following slides. So here is visualizing a deep learning network. Uh, like I mentioned, learning is happening in layers, and at each layer, the output or the representation can be seen here. This is an example of training a deep learning network to identify handwritten digits, so 0 to 9. Um, but handwritten digits, there's a lot of variation and randomness in how each person would write a letter or indicate a number or write a number. So in the initial layers, very localized patterns are learned using filters, and as you go from layer to layer, it gets aggregated, and uh, you learn the network learns more global patterns. And typically, uh, by the in this example, since this is an processing of an image, uh, a convolutional neural network is involved, and towards the end, uh, typically a two-dimensional all the information learned in a two-dimensional fashion uh, is converted to one-dimensional. uh, you can see here in this case it's layer 4, and then that the final layer leads to the output. And again, now let's uh, talk about the underlying algorithm, uh, and what we are trying to do in the process of learning. So this algorithm you see here is the learning algorithm. For example, you start with input data. You you pass the data through these layers, and you come up with an output. Like after the final layer, it does not have to be only two layers. There could be several layers. Sometimes you can even have hundreds of layers in a neural network when it comes to deep learning. But here this is just an just an indicative just example. So you go through the data goes through all the layers, and uh, it is trying to learn these weights. So after the first pass, the network makes a prediction, and the prediction is always compared with the actual value. So in the case of supervised learning, when you have labels or actual outputs, um, you can also call it the ground truth. You are comparing the predictions with the ground truth, and uh, creating a loss function. So you're calculating loss, or it is also referred to as error. So for example, it could be root mean square error. Let's say you are predicting a sensor output, and let's say your prediction says 0.1, but the actual value is 0.2. You calculate the difference, uh, and then you square it. You add that for each of the samples, and then you take the square root. So in a lot of in other problems, you could use a different loss function based on the problem you're trying to solve, and from there use an optimizer, which is what the optimizer is doing is trying to indicate how to update your weights based on the loss score, or it is looking at the overall loss and saying, should I increase the weights or should I decrease the weights, and how do I update the weights. Sometimes there are hundreds, and actually usually there are thousands and thousands, sometimes millions of weights involved in each deep learning neural network, and the optimizer is indicating how you update those weights in order to learn the right representation. So the process of uh, updating the weights based on the data is what uh, is called the learning, and that's why we are calling this machine learning. And um, training, when we say training a model or learning, this is what we mean, the process of updating the weights. So some examples where deep learning has really revolutionized a field or made significant progress compared to earlier state of the art. Like for example, before deep learning, um, how was how was the state of that discipline or that problem? For example, image classification. Um, every year, I'll give an example. There used to be some image processing challenges that, and every year the researchers working in those areas uh, come up with newer and newer approaches and algorithms and try to improve the accuracy of the algorithm. Um, before 2012, um, none of the algorithms uh, crossed 80% accuracy on a particular data set. Of course, the results depend on data set. I'm talking about a competition and a data set called ImageNet. Those who are interested can Google it and check it out later. But it is a data set with more than a million images and 50 categories of images. And the goal was to to uh, rightly predict which category each image falls under. And prior to deep learning, the best accuracy was around 75%. But in 2012, as soon as one of the competitors used deep learning, the accuracy crossed 80%. Uh, and in the subsequent years, there has been more, uh, more improvement, and then the accuracy even crossed 90%. So with respect to ImageNet, it is now considered a solved problem, and it was achieved because of deep learning. Similarly, speech recognition, it is good, but it is not perfect. Uh, those who have used um, Google Home or Alexa or any of these devices, they'll know that they work quite well, but they are not perfect. They still make a lot of errors. But it is a field that is evolving, and we're seeing continuous improvement. Eventually, they'll be very good. Similarly, handwriting recognition is was one of the earliest applications of deep learning, and uh, current state of the art handwriting recognition accuracies are close to perfect. So it is also a problem which can be thought of as a solved problem. And autonomous driving is one area where deep learning, you cannot do it without deep learning, and there's huge uh, research push from universities as well as companies in the autonomous driving space. Um, but again, it's still work in progress. There is no um, there is no company that has yet got a license to do fully autonomous uh, cars on the road. So this is still um, they're still trying to accumulate more miles, thereby collect more data continuously. improving their performance so that one day they will be as good as human beings at driving, so that they can get government's approval to to sell these autonomous driving cars. One of the areas where you're probably impacted by deep learning and not realize it yet is targeting of ads, whether on Google or on YouTube or anywhere. A lot of places the ad targeting is uses a lot of machine learning and in a lot of cases deep learning. And ad targeting and recommendation systems are some of the applications of deep learning which are already successful in making profits for a lot of companies. For example, those who watch Netflix, the recommendation system in Netflix is based on a lot of machine learning, and it has made Netflix really profitable because it's a successful application of machine learning in a widely consumed product. And um, advantages of deep learning, of course, way better performance. Like I just mentioned, some of the examples I have given. In certain applications which involve cognitive tasks, such as image recognition, object recognition, or natural language processing, um, you traditional machine learning methods do not do a good job, and there is no way you can do a good object recognition or natural language processing system today without using deep learning. And in fact, again, I'm assuming that you have seen machine learning your lectures before this lecture, since this is, if I'm not wrong, the last lecture in this series. Um, there is a data engineering or a feature engineering component to machine learning. That is, let's say, again, giving an example I've mentioned before. Let's say you have 300 features, and you don't know which one correlates with the output the most. Uh, we do a lot of feature engineering, that is deriving new variables from existing variables. Maybe create like take a square of a particular variable, cube, or product of two different variables or things like that. So when feature engineering was one of the most time consuming parts of traditional machine learning, and um, doing that is a manual process. It is also a trial and error process. So you don't know how long it's going to take. You don't know when or how you'll hit the right, find the right feature. And um, and also obviously you're spending a lot of time doing this manually. With deep learning, it completely eliminates that step. You do not do any feature engineering. The algorithm is learning this by itself. So you can think of deep learning as automating a certain time consuming part of machine learning. So even though the algorithm itself is more complicated, from a user perspective, whether you are um, in industry, um, or research, deep learning actually makes your job much easier. If you're trying to, let's say, solve a problem in healthcare, and you're trying to make a prediction, you will spend a lot less time working with deep learning, compared to machine learning as an overall project time. If you look at just the training time, the time which is used by the model to learn, a deep learning model takes longer to train than a machine learning model. As an example, in some of my projects, if I use simple machine learning, the model may be trained in less than a minute. but deep learning probably takes half an hour or 1 hour for that model to train on the given hardware. But if you think of the overall project, uh, probably deep learning saved you 10 days worth of time, which you would have spent on feature engineering. So it's much easier that way, and also uh, companies need to have a pipeline whenever they are dealing with data and machine learning. You've seen in one of the earlier slides where I showed the process or the flow of data. When you have to put that into production in a particular in a company, that data flow is converted into a pipeline, which is data going through these several stages. And when you use deep learning, you may require more computational power, but the uh, the pipeline itself is much simpler. You have a reduced stage in that pipeline, and uh, I'm not saying it is easy, but it makes the pipeline also more simple. So a quick note about uh, GPUs here, uh, which is the graphical processor units, which are very important, especially when you uh, use big data or large volumes of data requiring more processing power. Deep learning is entirely based on linear algebra and matrix multiplications. So GPUs tend to speed it up very significantly. In my own experience, on certain problems, if there was no GPU, especially using things like one of the terms you see here is LSTM. We'll see what it means a little later. But I've had to, when I put my model for training, I typically used to leave it overnight. I leave the lab in the evening, I put the model for training, I go home, and then next day morning, when I come back to the lab, the model is trained. It used to take overnight. But when I employ a GPU, the same training is typically like done in an hour. So it gives that much of a speed up, and it is more expensive, but um, of course, if you are in research, uh, if you are a well-funded research group, lot of research groups are updating to GPUs, and industry typically has better access to GPUs because they have more money. But the importance of GPUs cannot be understated. Um, the think about this: the algorithms which are very popular these days have been around almost for 30 years now. Since 1989, a convolutional neural network algorithm was proposed in 1989. It was popular in the 90s, but we did not have a revolution or everybody talking about deep learning and CNNs back then, because the results were not as impressive. But what changed in 2012, that suddenly deep learning started becoming so popular, especially because of the ImageNet competition I talked about. The reason is GPUs and the amount of data. One is, in the 90s, the researchers did not have as much data available. So probably there was no data set back then which had more than 1 million images. But today, with the proliferation of internet, it is very easy to achieve or collect millions of images. And with the application of GPUs, it becomes feasible to process all that data in a realistic time frame, uh, to be to, to either for a competition or for a real world application. It makes it feasible to apply deep learning. And right now, NVIDIA is a company that's investing big time into GPUs. Originally, they developed GPUs for gaming because a lot of games required um, matrix multiplication, lot of linear algebra behind the scenes, and uh, what started as something that supports gaming ended up helping academic research. So that was my uh, note about the significance of GPUs. But what does the GPU do? It's essentially helps improve parallel computing. Um, in, let's say, if you are multiplying 1,000 by 1,000 matrix with another same, similarly sized matrix, there are several subtasks that you need to multiply different numbers and then add them up. In a GPU, the huge multiplications are each done by a different core, and then you're combining those all those tasks, and then to create the overall multiplication. Um, this particular processes like this, which are highly parallelizable, uh, run very fast on GPUs. But if a task is not parallelizable, then a GPU may not be any better than a CPU or a regular processing unit. And like I mentioned, amount of data very important for deep learning. Uh, Sometimes, let's say, if you don't have enough images, it can look like, hey, I use deep learning, but this is not working very well. I am not getting good results. Deep learning algorithms are very data hungry. Uh, the more data you provide, the better it will perform. Um, Natural language processing applications, for example, uh, refers to text processing, text generation, and voice recognition, or language recognition, language translation. All these tasks, they were not as popular. Even though research was going on, they did not become so popular in industry and research until deep learning came about, where it was possible to obtain huge amounts of data. And finally, by 2012, the algorithms also got optimized quite significantly. For example, you have better activation functions. You'll see what an activation function is in further slides. But better, we have seen what the role of an optimizer is in the slide showing the flowchart, and there are different ways to optimize the weights or the learning process of the weights. Uh, During 90s and early 2000s, a lot of researchers who were working in deep learning and neural networks, they were trying to find better optimizers and better ways to initialize the weights. And all that research culminated in giving us more optimal, practically possible systems that can actually implement deep learning, and using this, huge data sets, be able to process those huge data sets in a realistic time to make it practical. So the algorithmic research, the computational research, the use cases, everything came together by uh, by the second decade uh, of this century to to make deep learning popular, and also help it revolutionize so many industries. A quick look at um, how does how does this algorithm optimize, uh, find the optimal point, or how does it, if you're learning from data, how do you find the most optimal representation of the data? How do you optimize the weights? So here is a building block of deep learning neural networks, that is a single neuron. In this case, you are seeing a neuron which is taking 25 inputs. So you can think of this as having 25 variables and uh, uh, one output variable. So you have um, the overall process of computation in this neuron can be summarized with this equation: uh, activation function of the dot product of the weights and input plus bias. So um, the weights um, the weights and bias are both um, parameters that are learned by the network. Um, and of course, in this equation, W is a matrix. The input is also seen as a matrix or an array. And then, of course, the bias term B is also another matrix. Typically, it's a single dimension, so it's a vector. And um, again, I'll not go more into the mathematics of it because it can or it should be a lecture by itself. But uh, this computational framework or with this neuron goes through the flowchart that you have seen in few slides ago, and those weights are continuously improved until the output is close enough to the desired output. So when the error reaches a certain minimum point, we stop the training. Excuse me. So how um, back propagation and gradient descent is a certain way of optimizing those weights or telling the network how to change those weights. And back propagation was very important in making neural networks successful. Um, this image shows here the what you have seen in the previous slide. This slide, this is a single neuron, and in the next slide, we are representing each neuron by just one node. So you can imagine um, if we show every connection, how complex this will be. Um, if there are 25 variables, you can imagine each one of them getting 25 inputs and then connecting the output to the next layer. So there is one path called the forward propagation and another called the backward propagation. So during the forward pass, the data is going in and the activations are calculated. Um, Again, remember the flowchart you've seen before. You calculate the loss, and the loss uh, is used to compute the derivatives um, at each node, and those derivatives are propagated back, giving the name of back propagation. Why do we need those derivatives? Um, okay, we have this training loop here for your reference because we are referring to this in several of the slides. So um, we all know from calculus that when the derivative becomes zero, we are at a point of minima or maxima. So uh, if you think of the error as a function, um, the error is a function of several parameters. And excuse me. So let's go back. So yeah, apologize for that. So where were we? In these when you have this function and you want to find the minima, you want to move the weights in such a direction that the value of the derivative reduces and you eventually reach uh, a zero of the derivative. Typically, you will never reach zero because it only happens in ideal cases, but in real world, there is a certain minima beyond which you cannot go further down. Um, because what I mean is the error will never become zero, but the derivative, we want to find the point where the derivative becomes zero. So we move the weights in the direction of the reducing derivative. So that's the reason for which we are trying to um, calculate the derivative, and back propagation is an approach that helps us very easily calculate those derivatives. So here you can see that in this graph, let's say this is a function, or this is a uh, plot of the error function, and we randomly initialize the weights. So when we initialize the weights, we may be here at the maxima, we may be somewhere in the middle, but or if you are lucky, you may initialize close to the minima. But the process that happens in this learning algorithm is, from these weights you calculate the derivative, then you change the weights, so you reduce the derivative, you move in the direction where the value of the derivative decreases, and with each step, uh, uh, a user defines this, how big a step you take. It is called uh, the learning rate. So if, let's say, you take a learning rate which is very big, then this step, if it is too big, maybe you will go from point t0 to this, to beyond t3. You want to end up at uh, t equals 3, the point t3. But if you take a very large learning rate, you may skip, or you might miss the minima. But if you take a very small step, then you are not reaching T3, you're taking small steps. Maybe you'll take 100 steps or 1,000 steps and you still don't reach T3. You're forever moving in very, very small steps. So finding the right learning rate is one of the optimization uh, steps, or a process. It is a process of optimizing the algorithm. It is driven by the user. So for example, if I'm training a network, I try different learning rates to see which is helping my algorithm converge faster to finding the minima. So this is the gradient descent. So since gradient here refers to the derivative, and since we are kind of descending down the curve until we find the minima, the name given is gradient descent. It's one way to remember it. So this slide here summarizes uh, what the backprop algorithm is doing. So to calculate the derivatives, uh, if you think about uh, the overall function of a neural network, let's say there are uh, three different layers, there are three different weight matrices. Um, let's say uh, W3 is the first layer. So the data goes through weights W3, W2, and W1, and it's a function of a function of a function. And uh, again, going back to calculus, using chain rule. Of course, we don't do all of this by hand, too many variables. It's all, in most of the implementation, it is done behind the scenes by a function or the library that you choose. But if you are implementing it um, fully by uh, implementing it from the scratch, also you will write some uh, code either in Python or MATLAB, on some programming language to compute, use this chain rule and compute it for every node. compute the derivative for each weight and move it in the right direction. So um, the cost function or the error function is uh, like I said, a function of a function or nested function, and we use the chain rule, and at each stage we calculate the derivative and propagate it back in the network. So this is a very important piece of the puzzle. And like I said, to go into the mathematics of it uh, needs a lot more time. So, but hopefully this helps you get an overall picture of what the algorithm is doing, and hopefully it piques your interest enough to study more about back propagation. So putting everything together, so this is like a example of a network that is trying to predict uh, time of failure for a particular equipment. Again, think about the initial system diagram you have seen. There are a lot of sensors collecting data from an equipment and being saved on the cloud, sensor data being consolidated and then fed into a deep learning network. Let's say there are M sensors, and then uh, you have here we are showing three layers. Of course, there are always there's always an input layer and an output layer, and everything in the middle is called a hidden layer. Here we have two hidden layers, and you can notice that every node in every layer is connected to every node in its subsequent layer. Um, of course, the output layers and input layers are connected only on one side, but like if you take a hidden layer, it is connected to the layer before it and after it, and each node in the layer is connected to each node in its neighboring layer. So again, to clarify some terminology, some papers refer to this as a fully connected network. Some papers can refer to this as a ANN or an artificial neural network, and some places you will see this being referred to as a DNN or a deep learning neural network. So uh, each, depending upon the number of inputs, there are um, there's a huge number of weights in each node, and like I said, the number of, even though we show only two hidden layers, it is very common to have tens of that is 10 or 20 or 30 layers. It is not uncommon, and there are networks which use hundreds of layers as well, even though I have not personally used them, but I have used networks which have the max I've seen is layer number in the 20s, 25 layers to 30 layers. But more advanced networks in recent times, especially in research, there are some networks which use 100 or 150 layers. Example is a network called ResNet or residual network. So uh, those who are interested can check it out. It is spelled RESNET, ResNet. So so uh, uh, apologize. So here, moving on, are you guys still able to hear me?
Yes, sir, you're pretty much audible.
Okay, okay. So so let's move on from a fully connected network to a convolutional neural network. Um, since I've mentioned the year 2012 before, that's when the popularity of deep learning really, spiked or uh, kicked off. And all the popularity of deep learning is really because of convolutional neural networks. They are most widely used neural network currently. And even if you see research literature, there are more papers on CNNs than any other type of network. And uh, especially when using images or arrays or um, two-dimensional, three-dimensional uh, images or matrices like data. CNNs are really effective, and they are much more efficient compared to fully connected networks. So local patterns in images. So for CNNs, uh, how it is more efficient compared to fully connected networks is um, you, there is a use of filters which extract data, or sorry, which extract information from an image, from different parts of an image, and um, as the same filter kind of scans across the image to extract this information, and it identifies certain local patterns. So as you can see in this image here, this is again an example of handwritten digit, and as the squares that you see on that in white are different positions of that filter which is being applied to extract those patterns. Uh, and these patterns are extracted and fed to the subsequent layer. So, I'm sorry. Okay. So, one of the things that we achieve by doing convolution or moving this filter, having a single filter scan across the entire network, is something called translation invariance, which is nothing but um, a pattern, um, whether it shows up in one part of the image or the other, you still identify that pattern. For example, if you have handwritten digit, you take an image of handwritten digit, whether the digit shows up in the left corner or the right corner or the bottom corner, right bottom corner, um, it's still, the output should still say number 4. So that is called translation invariance. This is one of the things that a convolutional network achieves, and it's very important when you're dealing with images. And if it was a fully connected network, again, another term that is used for fully connected network is a dense connected network. So uh, I've mentioned all of them. So if you see them in any of the articles, hopefully it doesn't confuse, and uh, we can remember it's the same thing. But uh, when we do a convolution operation, um, it achieves this translation invariance, whereas a fully connected network uses more resources to learn, and there is more redundancy in a fully connected network. Somehow it's skipping. Okay. This is an example. So I've mentioned earlier that there is a hierarchy involved in learning, and each subsequent layer learns a more meaningful representation. So it might sound very abstract earlier, but hopefully this image will help put it in perspective. For example, we are learning from an image, and it is an image of a cat, and the layer one applying these filters, those who are familiar with image processing, you must be familiar with applying different filters to images. So there are some filters which help you identify edges. um, there's some filters that uh, help you identify the boundaries and uh, corners and things like that. So in layer one, you identify very basic geometric shapes, and then from this, the next layer is trying to put some of these things together and learning that there is a circle that exists. There is there's something which is shaped like a nose that exists, something that is shaped like an ear, and then uh, again, this is just a indicative diagram. It's not, you could have 20 layers there where each one of them is progressively learning a more complicated shape until the final layer can tell from all these features that it is the image of a cat. Maybe this could be a problem where you're trying to identify the different images of different animals, and the network is probably trying to predict which animal it is. So um, that that is what we meant by a hierarchy. So in this case, because it's about an image, it is referred to as a spatial hierarchy. Um, you can extrapolate this to humans or any image. Let's say if you're taking example of an industry and we are trying to um, identify corrosion in a metal, the first layer will identify all the edges. The next layer will probably look at the pattern of those edges, and um, the final layer sees that if there are more than certain number of lines or a certain pattern, then it means that the corrosion has taken place in a metal. So it is the same hierarchical learning process, whichever problem we apply it to. So and then um, whenever you read about convolutional neural networks, we will run into um, a term called feature maps. What it refers to is, I have mentioned that uh, we extract features in layer, like we have several layers. The output of each layer is called a feature map. That is because we are extracting features, and then uh, we are putting it in a certain structure, and it's like a map of all the features. So it is referred by that name, and uh, every image or every input image has this has the same set of filters applied. Like I mentioned, there's usually not a single filter that is applied, but a set of filters, and each filter extracts a different feature or identifies a different pattern in the image, and then we are putting it all together for the next layer in form of a feature map. So um, when we put all the convolutional nodes together, and in each node a convolution process is taking place, uh, the um, for the feature map, the size of the patches that we extract are defined by the filter size. And um, like I mentioned, we use a set of filters, and the number of filters that we use will define the depth of a feature map. Um, there's a visualization of feature map coming up in the following slide, um, but then probably it will make more sense. But a filter, like I mentioned, is like a sliding window. Those who are familiar with DSP and image processing, whenever we apply a filter, the way it scans across the entire image is like a sliding window, window that slides over another uh, larger window in this case. Um, and by doing that, it covers the entire image and extracts patterns from all the different parts of that image. Okay, so yeah, this one shows how a feature map is created. So we say an input feature map because the input to one layer is coming from the output of the previous layer. So there is a uh, feature map that is being input to this layer, and in this layer, uh, Excuse me. Um, Apologize for that again. Just had to uh, uh, take a break for the sake of my voice. But so there is an input feature map, and uh, there is the three input patches. So these are like filters which are scanning, and in like it does it in different steps as like I mentioned, a moving window or a sliding window, and then there are three different uh, positions possible in that scanning process vertically. And when that happens, uh, if you remember, the equation had a dot product, and that dot product output of the dot product looks like this. The like I mentioned, there are three different patches being used. That's why the depth of the feature map is 3. So this is what we mean by the depth. You can see here. And for the once we have, for the sake of the next layer, all these three transformed patches are put together. So that is how you create the output feature map, where uh, the depth is decided by the number of uh, patches you use. Now, or the also referred to as filters. So here is an example of a realistic or a real world convolutional neural network. Another way of visualizing the overall network. In the previous slide, you saw how the feature map is created between two layers. So what you were seeing there is happening in between these two layers. But this is uh, an image of the overall convolutional neural network. For example, we start, here is an example, like I was mentioning, corrosion. Um, Here is an example of CNNs being applied to measure the extent of corrosion. So you have an input image is coming from a camera image, some sort of an image sensor. Here, uh, this could be like 30 or 60 filters being applied. So each two-dimensional image leads to one array, which is the output of a filter. And if we use 32 filters, the depth is 32 for this layer. And pooling is an let's say it's a function, or it's a process by which you consolidate the feature map. It is something like for every 4 by 4 matrix that you have, you take the average, for example. So it pulls the feature map together and reduces the dimension so that the computation can be more efficient. And also, in terms of machine learning, the advantage is it reduces overfitting of the network. And typically, pooling layers are used alternately with convolutional layers until we reach uh, a certain number of layers, or you reach a certain size of each feature map, and then the entire feature map is flattened to create a one-dimensional array, which is then uh, fed to a fully connected network. So typically in a convolutional neural network, there is a convolutional block and there is a fully connected block. The fully connected block again can have several layers, but typically in the networks I have used, the fully connected block is usually lean, having 2 or 3 layers. Um, Again, that has been my experience. It's not necessary that every one of them works like that. Even the number of convolutional layers, you can have 20 layers, 30 layers, or 100 convolutional layers, but the overall structure still will look like this. So we spent some time on CNN. Okay, this is the last slide related to CNNs. So the typical size of the filters are, usually 3 by 3 or a 5 by 5, something like that. Um, Usually the values in a filter are initialized randomly. So this might be a little surprising for those who work in image processing, um, because uh, deep learning is what you can call a stochastic process, where we are not defining beforehand what type of features are extracted, and we randomly initialize those filters even though the filter is applied to every input sample. So we um, one can ask, if we are initializing randomly, how will it extract meaningful features? What we are doing is we are randomly generating several filters. That's why we never use a 1 or 2 filters. Um, Typical examples I've seen, we use 30 filters, 60 filters, sometimes 500 filters to extract various different types of features from the images. And then uh, it's a statistical process where, by extracting so many features, some of them will be more meaningful than the others, and we eventually expect some of them to extract the right patterns and then give us the desired output. um, and of course, the initialization is random, but as during the learning process, those weights are updated. So we initialize randomly, but they we learn and move towards the right values for those weights, um, and uh, and then eventually learn and obtain the right filters. Um, like I mentioned, if it's a 3 by 3 filter, each one of the values in that filter is what we are referring to as the weights. So we've spent a few slides on convolutional neural networks. I had more slides for CNNs. For RNN and autoencoder, we just have a couple of slides, um, and then I have the slide where we had the data flow again, so that we can summarize and use the same slide to summarize this again. But RNNs are a type of neural network which is uh, really suitable for sequential data, such as uh, time series or text. So I mentioned natural language processing before. RNNs are used extensively in natural language processing, even though there is actually text processing and natural language processing is one of the most active areas of research right now. If you had asked me 4 years, 5 years ago, which area of deep learning is most active in research, I would have said CNNs. But if you ask me today, I'll say it is natural language processing. Of course, the most recent interest in NLPs is not around RNNs, but with something called as transformers. Again, it's beyond the scope of our discussion here, but those who are interested can check it out. There's a lot of research interest in using transformers for natural language processing. And coming back to RNNs, they are really suitable for sequential data, and they you can either you have there are two different types of RNNs. One is mapping sequence to a single output, like you see a time series and then you are predicting whether, um, for example, if you're analyzing stocks, for example, your output says whether the stock will increase tomorrow or decrease tomorrow, things like that. But you can also have a mapping of a sequence to sequence. For example, if we are using an RNN to do translation from one language to another, then you have to map a sentence to a sentence. So you are not mapping a sequence to a single output, but you are mapping a sequence to a sequence. And recurrent neural network, they call recurrent because they have internally they have loops that allow the information to persist over several time steps. That's why they don't consider only the current value of the sample, but also the previous values. And LSTM is the most popular type of RNN. Again, in RNNs, there are different types, and LSTM stands for long short-term memory. Again, LSTM architectures will be a discussion in itself, and I will leave it to you to explore LSTMs. Um, but here we will just see what a general or generic RNN looks like internally. This is for each node in an RNN. Of course, there are several such nodes in the overall network, but as you can see, this is a representation or a way of understanding RNNs. On the left side here, you see this is how it actually is, and this is just a way for us to understand the network. Um, you have, um, like I said, there is a certain memory or retention of information within an RNN for this the duration of the entire sequence, where the output of this network in a previous time step is being fed back to the network to the node. That's why you can imagine it when you unroll it like a sequence of nodes where the input to one node is being given as the output of one node is being given as input to the next node. But again, keep in mind that there are several nodes like this within the overall network. Um, they are usually again in layers. The fact that there are several layers and several nodes in each layer doesn't change whether it's a CNN, RNN, or an autoencoder. Again, in this discussion, I'm sticking to only these three. There are other types of architectures as well, but two reasons. One is CNN, RNN, and autoencoder are the most popular architectures, and also in the context that I have started this discussion around IoT and industrial IoT. Um, these are the three most common architectures I have seen in applications related to industrial IoT. Um, in fact, I have published a review paper on the same topic of deep learning being used in industrial IoT, and all the research that I have seen falls broadly into the buckets of CNN, RNN, and autoencoders. Of course, there are exceptions. There are other more advanced types of architectures used, but these are the most common, and this covers most of the ground for us. So, how are we doing time wise? Um, I think we are over time, right, Nagendra? Okay, almost done. So
Yes, sir.
I'm wrapping, and this
Yes,
is
sir.
the last couple of slides. I'll wrap up now. Um, so an autoencoder, like in the beginning, I mentioned that a neural network can be seen as encoding the data. If you try to recover your original data from the encoded version, it's a process of decoding. An autoencoder does a combination of both. It is trying to encode your data and then get your data back as well. But during the process, it introduces a bottleneck by having the hidden layers have less number of nodes than the input and output. And this way, we learn a very efficient representation of the data. And for example, if it is sensor data, this is a great architecture to do denoising of the data. and uh, the um, when you introduce the bottleneck, it helps you capture the signal and leave out the noise. Again, the mathematics behind it uh, is very deep, so I'm just touching the surface here. This is pretty much our last slide. uh, you have seen this before. This is our slide number 3. I brought it again here because of this table. Hopefully, hopefully at this point it makes more sense why we use different deep learning architectures for different tasks. If we are using for example, detection of structural damage it needs images. So when there is images, we use CNNs. Forecasting future sensor output is usually a time series. You have a time series, think of RNN, but application of fully connected network and CNN is also possible in forecasting. So if the sensor is an image sensor and you are trying to forecast, then you can use a CNN. And wherever in an autoencoder, your your input is itself the output, so there is no need for labels. So it is very suitable for unsupervised learning, denoising, dimensionality reduction, and pre-training of a network means just extracting features from data. And autoencoders are very good for that purpose as well. So I hope this summary of these architectures helps you understand why we use those architectures for different tasks. And that's the references, all the material that I have referred to uh, for this for these slides for this lecture. That's the last slide. Sorry for going over time. Uh, you can ask me any questions if you have. I'll answer them to the best of my knowledge.
Okay, sir. Thank you very much. So we have already overstood the time
Yeah,
limit.
yeah.
So I'm going to take only 3 questions. The first
Sure.
question is, uh, sir, attack detection in IoT is fully developed or is still there is scope of research?
So when you say attack detection, you're talking about cyber security, right? So um, cyber security itself, there is a lot of scope for research. It is an ever evolving field. If you are interested in research or industry applying machine learning or deep learning to cyber security, I don't think there is an end to it. I don't see it will not be considered a solved problem. I don't think in years to come. So the answer is no. It's not a solved problem. There is a lot of scope for further research in cyber security, attack detection using deep learning.
Okay, sir. I'm taking the next question.
Sure.
How can we make the output of deep learning network more explainable and understandable rather than as a black box?
Very good question. It is coming from someone who already knows enough about deep learning. So like you've seen here I've mentioned earlier that if you use traditional machine learning, you engineer the features so you know what are the features going in. But in deep learning, the algorithm is learning the features itself. So we do not, it is hard to explain which features are making more sense. But how to explain deep learning is an active field of research, which means uh, there are few techniques that I know of. For example, in images, in this textbook, you can see here itself. There is a section where there is sample code for you to visualize the images as a heat map. So, for example, if you can see for the output what is the most important part of that image, which is helping you identify. Like for example, if you're identifying it as a cat, you can see which part of the image really help the algorithm to um, identify that it is a cat. But there are some techniques like that, but it's again a very big research area. which means that there is no simple answer to that. But uh, the, the the science behind deep learning is not 100% uh, uh, available, or it is still in the process of being discovered. The researchers found that if when you arrange these nodes a certain way, they give great output, but why that is happening is not fully answered at the moment. That is why when you're trying to train a network and optimize it, the hyperparameters, you optimize them in a trial and error fashion. Like I mentioned, uh, the learning rate, you are trying different learning rates to see which one works the best, but it is not there is no better way of doing it as of now. As we understand these networks more, there will be probably a more efficient way to do it. uh, I hope I answered your question.
Okay, sir. I'm taking the last question. What is convolution and pool?
Convolution and pool. Okay, let's go back to the convolutional neural network image. Sorry, I shot past. There we go. It was this slide. And um, convolution operation is um, this is an extension of if you've studied signals and systems, we study the process of convolution of two different signals. In this case, imagine the signals being a two-dimensional image, signal being coming from the image data. So if you have a filter 3 by 3, it is another spatial signal. Basically, you extend the definition of convolution to a spatial two-dimensional convolution. And what it in a typical one-dimensional convolution, you take two signals, and then you invert one of them, and then like a sliding window, you hold one of the signals constant, you move the other, and at every position you calculate a particular product. So here you do the same thing. You hold one of the images constant, you are moving this filter across the image. At every position you calculate a certain product, and then you are aggregating all of that data. Pooling is a way of, let's say I started with an image which is 1000 pixels by 1000 pixels, and at every stage of convolution it is computationally very intensive. uh, so what pooling does is, uh, it kind of aggregates reduces the dimension of the image. uh, After the first convolution, your feature map looks like uh, uh, several two-dimensional images, and from that image you take every small piece of 4 by 4 matrix, and then you take the average of it and replace it by a single pixel. So um, a 1000 by 1000 pixel image after pooling becomes 250 by 250 pixel by 250 pixel. So significantly reduces the size. You lose some granularity, but in the whole scheme of machine learning, it is actually an advantage because it reduces overfitting and improves your computational efficiency. So that's what pooling is doing. And it again, it happens in layers. So there's a layer of convolutional nodes, and then you do pooling, and then you have another layer of convolutional nodes, and then you do pooling again. So that's why it is represented like this.
Okay, so I hope there is no more question. Thank you, sir, for very informative lecture.
Problem. I hope it was useful to at
Yes, sir.
least some of
Yes.
you.
Okay. Thank you very much, sir.
Yep. Thank you.
Uh, okay, so we are having exam starting at 7:30. Okay, one more thing, definitely, who if you want to directly contact Srikant sir, he has given his email ID, so you can directly contact him.
Okay, thank you everyone. I'm
Okay,
dropping out
thank you,
now.
sir. Thank
Thank
you. Okay, bye. Sir. Now, so we are having exam from 7:30. So there are two sections in exam. One section is the personal information, and there you need to fill uh, the your registered email ID, registered name, right? Okay. Once again, I thank you all for joining the all those sessions. I also would like to thank AICT for giving me this opportunity and also sponsoring the sessions. I also like to thank Director IIIT Pune for this opportunity. Thank you, everyone.